at Burke Neurological Institute, and we're here with Raj, who is the CEO, and he's going to show us some of the very interesting and amazing things they're doing.
So here at the Burke Neurological Institute, the main focus of our efforts are to try to figure out how to repair the brain and the spinal cord in diseases like stroke, spinal cord injury, traumatic brain injury, Alzheimer's disease, and Parkinson's disease. Neurological conditions are the #1 cause of disability in the United States. A recent statistic that suggests if you include tension headache, that 180 million people in the United States experience some short-term or long-term disability from a neurological condition. And there are 340 million people in the US, so it's a large number. We're going to take you through our laboratories. This is the Hewitt building. It's a building where we have our library and a lot of offices, and most of the science actually goes on through these doors. So this is the laboratory of Abid Husseini, who you'll be talking to.
Yeah.
And Abid's lab focuses on why it is in Alzheimer's disease that people forget how to get home. They'll go to places that they've been thousands of times and they'll forget how to get there. Why is this area of the brain so vulnerable?
Right.
If you can figure out how to stop Alzheimer's where it starts, then you can potentially treat the disease.
Right.
So this is an electrophysiology rig. As you know, our brains are just filled with electrical activity, and so we're able to actually study what goes awry in diseases like cognitive aging and stroke and Alzheimer's disease with the activity of the brain and how we can normalize it. So this is what's called an amplifier, and it's a stimulator and an amplifier. So the idea is you can take a slice of brain tissue and you can stimulate it in a particular way that is supposed to enhance connections between different parts of the brain. And that's really what learning and memory is about, is enhancing these connections. Right. So in many diseases, with the appropriate stimulation, those strengthening of connections don't happen.
When someone donates their body to science, how much use can you get out of the brain before you can't really test it anymore?
There are certain things that have to happen in order for that tissue to be optimally useful. Between the time that someone dies and the time that the brain is removed has to be very short. But I think what's really exciting is that there are huge advances in imaging techniques, non-invasive imaging techniques, that allow us to understand what's happening in the brain years before disease starts.
Right.
And I think that's particularly exciting because it's going to give us the opportunity to start treatments much earlier. And many of those treatments may not necessarily be conventional drugs, but it'll be like eating the right diet, exercising, all of the things that are actually well established to protect us from dementia.
Right, right.
We're going to go downstairs and I'll show you a piece of equipment which is really going to help us to understand how to use brain-computer interfacing to restore vision.
Wow, that's a microscope.
So it's called a 2-photon microscope. Basically, this allows us to image deep into the brain and record activity from thousands of neurons at the same time while processing visual information. So we have a couple of different lasers. These large boxes here are actually the lasers themselves. They are operating at different wavelengths of light. We actually can't see them. They're in the near-infrared spectrum. They are routed across the table. You see all these mirrors routing and different optical elements to combine the beams and prepare the beams to go into the microscope. So you can see we're combining several different lasers. Those are to do both imaging and very precise stimulation of neural activity. So we can ask questions about what patterns of activity drive visual experience and how we can understand how the brain processes that information.
This is all part of one microscope, yes?
Right, yeah. So it's all part of one microscope, but the microscope does several different things. But it allows us to stimulate, essentially create images that we beam into the brain to stimulate specific neurons. So it's a technique called optogenetics. We insert these what are called opsons into cells genetically, and that makes them light sensitive. That allows us to then use, in this case, lasers and holographics, so we actually create patterns of light to stimulate specific cells. So normally they wouldn't respond to the light, but we make them respond to the light with the proteins that we express. Recently, we've learned that we can do a decent job of predicting the activity of, in this case, the visual cortex, as they're viewing natural images. So unlike what we typically have done are these very basic patterns, we're now starting to look at how the brain responds to natural images that they might see in the natural world. And that's allowing us to make better predictions about how the brain's going to respond, and then make better experiments, essentially, design better experiments that we can use to test those models for how that information is encoded.
Raj clarified earlier, but just to have it from you as well, the ultimate goal here is to do what?
Yeah, so we have two main goals. From the science perspective, we want to understand how the brain is organized and how this basically works, how visual information is computed and represented and conveyed in the brain. But that will ultimately allow us to use that information, and even perhaps some of these technologies or some other technologies that are inspired by this, to restore vision in the case of vision loss.
Okay, the million-dollar question. What's your prediction as to how many years away you would be from having that final product available?
There are ongoing efforts by the field, by companies, to and actually successfully to have restored some sight in people that have gone blind. So it's certainly years off. I mean, we're just learning about how the brain encodes at this level of resolution. But I could imagine hopefully in my lifetime, I'll be able to see it happen.